Alright, so in this video we're going to talk about Dalton's law, and Dalton's law deals with situations in which you've got more than one gas in a container. So if you look at Dalton's law, basically if you have a mixture of gases, the partial pressure for each gas is equal to the total pressure. So basically if you have a mixture of different gases, and let's say that the pressure of the first gas is 1 atmosphere, and the pressure of the second is 2, and then the pressure of the third is 1, the total pressure would be equal to the sum of those pressures. So it would be equal to 4 atmospheres. So anytime that you've got a mixture of gases, the pressure from each gas, if you take the sum of the pressure of each of those gases, that's going to equal the total pressure that's inside that container. So if you have 3 liters of carbon monoxide gas at a pressure of 199 kilopascals and 1 liter of carbon dioxide at a pressure of 300 kilopascals, and they're injected into a 1.25 liter container, if you assume there's no reaction, what is the total pressure in the container? Okay, so knowing what you know now, a lot of you would be tempted to say, okay, 199 is the pressure of the carbon monoxide, and 300 kilopascals is the pressure of the carbon dioxide, and then you might just add them together. And that would be correct, except there's something else going on here too. So let's pull out all the information. So for carbon monoxide, or CO, my volume is 3 liters. It also tells me the pressure at that volume is 199 kilopascals. All right, and then it says that for carbon dioxide, my volume is 1 liter, and the pressure here is 300 kilopascals. All right, well, it's saying that both of these gases are injected into a 1.25 liter container. So my volume is changing here. So this is my V1. And this is my new volume. I'm injecting both of these gases into a smaller container. Well, if I do this for this gas, well, it's going to a smaller volume, which means that the pressure should be increasing. So the pressure is actually not going to be 199, it's going to be a higher number because I'm moving it into a smaller container. So the same thing here. Carbon dioxide is also injected into this container. So the new volume here is 1.25 liters. So my initial volume was 1. Since my volume actually increased here, in this case, my pressure is going to decrease here. So what I need to do is I actually need to find the pressure for each of these gases, and then at that point I can figure out what the total pressure inside the new container should be. So I know that something is changing here, so really I'm looking at the combined gas law. And since we're not concerned about the pressure should, it's not mentioned here, so it's probably being held constant. I don't really need to worry about the N here either because I'm just looking at this one gas, so the amount of this one particular gas should not be changing. So I'm going to be using this formula, P1 times V1 is equal to P2 times V2. So I'm going to do that for each of these gases, and then I'm going to combine the partial pressures. So P1 is 199 here, V1 is 3, and that's equal to the P2, which is unknown, times V2. Oh, which we do know, which is 1.25. All right, so if I go through this, do my calculations, $597, that's equal to P2 times 1.25. So P2 is equal to 477.6 kilopascals. All right, so now that is just the pressure of carbon monoxide. So now I need to find the pressure of carbon dioxide. So I'm going to do the same thing essentially. P1 is 300 here. V1 is 1, and that's equal to P2, which is unknown, and multiplied by the new volume of 1.25. So if I do the math here, 300 divided by 1.25 gives me 240 kilopascals. So if I look at the information here, for carbon monoxide, the pressure should be going up because the volume is getting smaller, and then for carbon dioxide, the pressure should be going down, which is what happened. So I have the pressure for carbon dioxide here, and then for carbon monoxide here, and then basically for my total pressure, I'm just going to take the pressure of the gases and add them together. So my total pressure is equal to 477.6 plus 240 here. All right, so it's 717.6 kilopascals. So that's my total pressure here. All right, so let's look at another type of example. All right, so a mixture of 2 moles of hydrogen, 3 moles of ammonia, 4 moles of CO2, and 5 moles of N2 exert a total pressure of 800. What is the partial pressure of each gas? Okay, so you know inside this container, you've got a mixture of different gases. So inside your container, you've got hydrogen gas, you've got ammonia, you have CO2, and then you also have N2. Well, the total pressure for the inside that container is equal to 800. So I want to figure out the pressure that each gas exerts. So really what I need to do is I need to find the percentage of each gas. So I was given an amount of moles for each one. So what I can do is I can find the percentage with the moles. So my hydrogen gas, I have 2 moles. For my ammonia, which is 3 moles. And then for my CO2, I have 4 moles. And then for N2, I have 5. Okay, so what I will do is I will find the percentage for each gas. And really what it's called exactly is called a mole fraction, but really it's a percentage. So the total number of moles here is 2 plus 3, which is 5, plus the other 5 here, that's 10, plus 4 here. So there are total 14 moles total. And typically when you do a percentage, moles is a good way to calculate your percentage. So what I'm going to do, I'm going to find the mole fraction for each one. So it's going to be the moles of hydrogen, which is 2, divided by 14. So that will give me 2 divided by 14 will give me about 0.14. And then I'm going to multiply that by my total pressure of 800. So you're going to find the mole fraction here and then just multiply it by the total pressure. So that's multiplied by 800. So the pressure for this one, it will be 114.28. So 114 for hydrogen. And this is going to be torr. All right, so let's do the same thing for each one. So take the number of moles of ammonia, which is 3, divide that by the total number of moles, and then multiply that by the total pressure. So 3 divided by 14 times 800 will give me 171 here, and that's going to be torr. All right, so now let's do it for carbon dioxide. So moles of carbon dioxide divided by the total moles times the total pressure. So it's 4 divided by 14 times 800. So it's going to give me 228.5. So really that's going to be 229 torr. I'm rounding to sig figs here. All right, so now do the same thing for nitrogen. So it's 5 moles of nitrogen divided by 14 total moles multiplied by the total pressure. That'll give me 285.7 or 286 torr. All right, so when you have an example like this and you're trying to figure out the pressure of each gas, get the mole fraction. Which is really a percentage, and then just multiply it by the total pressure. That little t is for total. All right, so now let's look at another example. Okay, so this one was a little bit different than the one I did in class because it's more representative of something you're going to see. So I have a 250 milliliter sample of oxygen that weighs 0.326 grams and it's collected over water at 26 degrees Celsius. What is the pressure of the dry gas alone? Okay, so basically in a lab, whenever we collect gases, that's usually done with water displacement. So that means that you'll have some sort of vessel that's full of water, and then you have the gas being released into that vessel, which pushes the water out. So the gas is being collected over water. Well, what ends up happening is that you have this vessel. So you have some sort of apparatus where you're collecting a gas and you fill it with water. Well, the gas that you're creating will go into this vessel and then basically displace the water out, and then you'll have some gas up here and then you'll have it over water. Well, what ends up happening is that there's actually going to be some water molecules in with that gas. So you have to account for the pressure that the water vapor provides as well. So you have to subtract out the water vapor if you collect a gas over water. All right, so first thing we're going to do, we're going to pull out the information here. I would have a 250 milliliter sample of oxygen, and it weighs 0.326 grams, and that's going to be my N, or my number of moles, and that's collected over water at 25 degrees Celsius. So 25 degrees Celsius is my temperature. And what is the pressure? So I need the pressure of just O2, the dry gas alone, so the oxygen gas without the water vapor. Basically, if you look at this, nothing is changing here. So if nothing is changing, we're dealing with a gas, it's probably PV equals nRT. So we can find the pressure, but if we were to do this, this would be the pressure inside the entire container. That would give you the total pressure. It's not going to give you the pressure of the oxygen by itself. So it also tells me that the pressure of the water vapor at that temperature is 23.8 torr. So once I find my total pressure, I can just simply subtract out my pressure of water. All right, so if I'm going to do this, everything has to match the constants in the R, or the units in the R. All right, so my volume would actually be 0.25 liters because it needs to match R. My number of grams needs to be converted to moles. So O2, oxygen gas, would be 32 grams. All right, so let's go ahead. Look at this. It's 0.326 divided by 32. That's going to give me 0.01 moles. 25 degrees Celsius is actually 298 Kelvin. So now I'm going to find the pressure of the entire container, so the pressure of all the gases together, and then I can go back and figure out what the pressure of the O2 is by itself. So P is unknown, V is 0.25, N is 0.01, R is 0.0821, and then your T is 298. All right, so so I get 0.244 here. My pen is confused about what I'm doing. Okay, so now take that divided by 0.25. You get, my pressure is 0.978 atmosphere, so roughly 1 atmosphere. So in order to get the last part, I need to get my pressure of my oxygen gas by itself. Well, the pressure of the water vapors and torrs, so I need to convert one of them. It really doesn't matter which one I convert. So let's just do this one. So 1 ATM over 760 torr. So 23.8 divided by 760. Give me 0.0313. All right, so that is ATMs. So now this is the total pressure inside the container. I want the oxygen gas by itself. So I'm going to take 0.978, subtract the water vapor pressure out. So you will get 0.9467 ATMs. This is the pressure of oxygen by itself. All right,